All right, guys, let's talk transformers real quick. By the end of this video, you're going to be able to do math with transformers. So you're going to be able to figure out input or output voltage, input or output current, and you'll be able to get a good handle on number of coils or number of turns. All that stuff might not make sense yet, but it will. So here's what a transformer is. In a nutshell, it's an electrical device that changes a voltage and a current. It only works with AC power as far as we're concerned. And how it works is the AC, the alternating current in our primary coil, makes a flip-flopping magnetic field. And if you remember, magnetic field can cause the movement of electrons in a wire. That's called induction. So inducing or causing the movement of electrons by making that magnetic field. So here I do not have an AC power source, folks. I've got a DC power source. This is a battery. And in this simulation, it's just like a D-cell battery. The electrons in this coil of wire are all going the same direction. And they don't switch directions. Remember, the whole point of direct current is it's a one-way only flow of electrons. And we can also see these little red and white diamond shapes. These are showing us what the magnetic field looks like. So the magnetic field is not changing. Now, if I move this battery around, the magnetic field changes a little bit. But we can't get electrons to move in our receiving wire. The reason why? If the magnetic field is always the same, that means that the force on all these electrons is always the same. It's not going to cause movement. We need a flip-flop. So I'm going to change this guy to an AC power source. And now we've got electrons in alternating current that change directions. So they flow one way for a little bit, then they flow the opposite way for a little bit, and then they just keep doing that. So I've got this thing as turned up as I can. It's 100% power. And you can see here, when the electrons move one way, my little compass needle flips one way. And when they change directions, my little compass needle also changes directions. Really, really simple idea. So coil of wire, electrons go through one way, magnetic field in one direction. When the electrons change direction, the magnetic field changes directions. And we can see that it actually causes wobbles in the electrons of the wire. And we can even see that it makes our little light bulb turn on a little bit. So I'm going to turn off the little flippy floppy magnetic field, and I'm going to get this just a little bit smaller, and I'm going to get this a lot closer. Because remember, the farther away you are from a field, the weaker it is. So that means that when I'm over here, I'm too far away for the magnetic field being caused by this power supply to really do much. And you might remember that as the inverse square law. So if I double my distance between the two objects in the field that I care about, the source of the field and whatever's being affected by the field, you double the distance, you divide the strength of the field by 4. And every time, so that means field strength falls off very quick. So over here, I'm not really getting any action on my light bulb. If I get it a little bit closer, we can get a tiny amount. If I get it even closer, we get much more. And then of course, if I put it right over top, we really, really, really have a bright light bulb, and it flashes on and off. So what's happening? The electrons are changing directions in here. It causes a flip-floppy magnetic field. The flip-floppy magnetic field causes the electrons in the receiving coil to go one direction and then the other. These devices are everywhere. If you've ever plugged anything into the wall, and you know how there's usually those kind of medium size, they're like just a little bit smaller than a pack of cards, kind of black plastic box where the plug-in part is. That's a transformer. There's a transformer in there because all of your electrical devices, they rely on different voltages and different currents. So the voltage that you get out of your wall is 120 volts. Not everything wants to be operating at 120 volts. So we need transformers to modify the voltage. And so not only that, but the flippy flops of electrons that are coming out of your wall in alternating current in your plugins, that is changing really fast. Now here, this is changing about 1.5 times a second. The stuff that you get out of the wall socket is changing. It's flip-flopping 60 times a second. So if I crank up the speed here, this is going at about 4 times per second. And you can see that the light bulb is flashing on and off a lot more rapidly. So the higher the frequency of the flip-flops, the faster the switching on and off of the device. So that's how electrical devices work in a nutshell, based on the electrons moving through them in a particular way. There's other stuff that's going on. You can change AC into DC and DC into AC, etc. We're not going to talk about that. That's not the purview of this course. But I'm going to kill this simulation and let's talk about the math of ideal transformers. So yeah, we've already established a flip-flopping magnetic field that is created because of electrical AC power causes or induces alternating current in the receiving coil, in the secondary coil. So here is a schematic of what this looks like. So you've got a magnetic core. That's a kind of material. It's usually a ferrous magnet, I think. Or it's magnetic, so it would be like an iron core. And we wrap a primary coil of wire around one side, and we wrap a secondary coil around the other. So you might notice P and S here. So there's 3 things that we care about in a transformer. The first is a variable or a number that we call N. And that's simply how many coil turns we have. So on this coil here, I could count 1, 2, 3, 4. On this coil, the secondary, I would count 1, 2, 3. Now the other 2 letters that we care about, or the other 2 variables, are things that we've seen before. I'm pretty sure everybody by this point knows what V stands for, and that's voltage. And I'm pretty sure everyone knows now, and this is the awkward one, that I stands for current. There's 2 other parts of the formula that we care about. They're lowercase or subscript p and subscript s. Now, it doesn't take a genius to look at our transformer situation and say, oh, I think P is probably primary and S is probably secondary. If that's the way your brain is thinking, you're 100% right. So in a transformer question, you're going to be given 3 pieces of information, and you're going to need to figure out the 4th piece of information. So let's do a quick example question. Let's actually use this guy right here. So I'll do one with, I suppose, voltage. Really simple. The simplest question I could even think of. We're going to throw 5 volts into this transformer. Then we have to find out what the voltage output is. In other words, the voltage secondary. So whenever we do a question like this, we need to write down all the stuff we know. Okay, I know that the voltage primary is 5.0 volt. I know that voltage secondary is what we are trying to figure out. I know my number of turns on this coil is 4 because I counted it myself. By the way, it has no unit because you're counting stuff. It's like, how many of this thing do you have? Well, I've got 4. And I know that my number of coils on the, whoops, that's awkward. Let's undo that. Let's do a better S. On the secondary is 3. So I look at my formula setup. Now, when you have multiple formulas that are all equal to each other, it shouldn't be too tricky. You want to pick the ones that we have the information to solve. So in this case, are we going to use IS and IP? Certainly not. We're going to use these guys here. So I'm going to write the formula down, NP divided by NS equals VP divided by VS. I'm not going to throw my numbers in there yet. I know it's tempting, but what I want to do is get rid of all of the fractions because I know y'all hate fractions. Remember, in order to do fractions, you just cross multiply. So I'm going to have NP times VS equals NS times VP. The reason why I'm doing this intermediate step, I'm trying to find voltage secondary. So I'm trying to find VS. What students sometimes do, and it's, I mean, no harm, no foul on their part, except I guess it is harm and foul because it's wrong. They'll try to solve for VS while it's still on the bottom. Solving denominators is a pain in the butt. Don't do it. Instead, get all the denominators off the bottom by cross multiplying. So how do we isolate VS now? Piece of cake. I'm going to divide both sides by NP. So then we're allowed to do our removal of part of the formula. And there we go. VS equals NSVP over NP. Now I toss my numbers in. So NS was 3. Voltage primary was 5.0 volt. And NP was 4. So this is 15 volts divided by 4. We're going to have 2 significant digits here because we have 2 significant digits in our voltage. Do not use significant digits for the number of turns. It doesn't matter. It's not going to mess you up. So I get 3.75 volts, which I only get to spend 2 sig digs. So 3.75 is going to round to 3.8 volts. Now we have to ask ourselves, is this a step up transformer or is it a step down transformer? My voltage went down. I had a 5 volt input, but I only got a 3.8 volt output. So this would be a step down transformer. Let's do another example. I'm going to delete that because we're going to be using something different. So let's use a different set of coils. So I'll say so 6.25 amps is put into a primary coil with 39 turns. The secondary coil has 125 turns. What is the secondary current? So I go up here and I look at my formulas, and this time I'm going to be using I have current and I have turns. So here's current and here's turns. So I ignore the middle. So I'm going to have NP over NS equals IS over IP. So NP over NS equals IS over IP. So I'm going to cross multiply. So I have NPIP equals NSIS. NSIS. So let us, and I'm just going to type these because it's going to be quicker. NP, the number of coils on the primary, or turns on the primary coil, is 39. And S, the number of turns on the secondary, is 125. My IP is 6.25 amps, and my IS is I don't know, because that's what the question's trying to get me to do. Back to our formula, we need to isolate for secondary current. That's IS, which means I'm going to have to do a tiny bit of algebra. If I want IS to be alone, I have to divide both sides by NS. That allows us to get rid of NS, meaning NPIP over NS equals IS. That's our formula. So now we can plug and chug the numbers. NP, primary coil, 39 turns. IP, primary current, 6.25 amp. And NS, number of secondaries, that's 125 turns. So I do my math, and I remember I can only record to 3 sig digs divided by 125 gives me 1.95 amps. And amazingly enough, that actually is, like, I didn't have to do any rounding or anything. That's just how it comes out. So I'd say the second coil is going to have an output of 1.95 amps. If we were to do the same thing with the voltage, we could do the same kind of question. The only thing you need to keep track of is S is on top, P is on the bottom for current, but it's P is on top and S is on the bottom for number of turns and voltage. So I hope that slightly helps you understand the concept of transformers for AC.